Hey everyone, this video is going to be on actually running your CFD simulation in Ansys, everything from setup to simulation to looking at your results. Before I begin though, there's one thing I forgot to mention in one of the previous videos. You're not limited to creating your 2D domain from scratch, like how we did, right? Drawing out the airfoils. If you guys want to, a fun thing to start with would be almost a cross-section of the car, a 2D slice of it. And that'd be a fun thing to sort of familiarize yourself with the way the airflow behaves around the car at different sections. So for example, if I go into section view on this model is the aerodynamic model that we used in simulations last year. It's simplified, so this entire chassis is one big body. So there's no chassis tubes or steering wheel or anything like that because we wanted to simplify it as much as possible, but maintain certain features that will affect your airflow significantly, like your wheels, of course, and the suspension rods. Alright, so let's say we go into a section view and you want to take a look at sort of a section slice of the car for 2D CFD. So I could go straight down the center like this, and you'll sort of get an idea of what air might look like if you take a slice out of this section. How will it flow when it gets stuck underneath the nose cone here, and how will it behave with the driver's head blocking much of the air that hits the rear wing. You can take any slice, any section. I think an interesting one that I want to look at is sort of the airflow. Let's see. Roughly over here-ish, if you take the cut, you'll see we get the two elements of the front wing, part of the under tray, and all three elements of the rear wing. So that would be a pretty good section to look at. So I have the section view taken out. We need to generate a plane on which to sort of project this view. So back in the assembly view, I'm going to go to reference geometry, plane. Let's see. First reference. Actually, let me make sure you guys know where to find this. So that's all in Google Drive over here. So it'll be in Drive. It'll be in the Aero folder of TR20 design on train racing, and it should be in full car CFD CAD. Updated CFD CAD, right? So Carlos and Grace worked on this. Carlos, Grace, and Leo worked on this over the summer. And over here in CAD, you can download all these files, and there should be this assembly that you can use as a reference. All right, so back over here, we're going to create a plane that roughly coincides with this section view that we generated. So I want it to be parallel to the front plane, or the center line plane. And the next I want to set this offset distance down here, offset distance. I'm going to flip the offset to move it in this direction. I got the measurements pretty close last time, so it's like 15 inches is a little too far, so there. All right, so 14.35 inches seems pretty close to this section. I'll hit create or OK. And we'll have our plane. If we exit the section view is just visual, it doesn't actually change anything. So that's what we needed to create the plane. And next we have to sort of project all the lines that intersect the plane onto the sketch. So we're going to create a sketch, and it's going to be convert entities, but instead of just straight convert entities, you're actually going to use intersection curve. So what that does is it takes the curve that intersects with the plane that you're sketching on. So we're sketching on this plane, and then whatever entities that we select, it'll project that curve. All right, so this is going to be a little tedious. Just got to click all of the parts. Let me just hit OK to begin with. There. And you can see those curves starting to begin. Select entities. I got to keep going. Let's see if I can choose bodies. All right. These three on the rear wing will be easy. Just got to make sure you select all the faces. Alright, so you see the rear wing, we're missing this one edge down here on the gurney. So Sorry guys, I'm hoping there's a better way to do this. Maybe if you use one of these selection tools up here, you can select the entire body. Surface bodies, filter solid bodies. Okay, so if I change my selection to solid bodies by clicking that, I should be able to, for example, select the whole under tray, hit intersect, boom, there's our intersection curve. Okay, so that would be a much faster way to do it. If I exit the sketch, then I can take the sketch, copy, and if we go to our 2D domain that we created, I'm just going to paste it here for no reason other than I had it open. But we can paste that sketch and right, you'll see there's like that representation. I'm going to undo. Just make sure you have like your orientations right or something. Let's see. Let's paste. Great. So I have the sketch pasted, and then again, you can go through the same process as before. Let me just suppress this guy real quick. Damn. I'm just going to hide it. But we have this new sketch that we imported, and once again, you have to go through your whole process of making the fluid domain around it. Right. Except this time, you need to set a distance from the ground. So let's say I know that the distance from the ground to this airfoil is, I don't know, you can measure it out in the model, but I think it was somewhere around like 2.35 inches. So 2.35. Hello? Where'd you go? Cool. Alright, so then I want this guy to be tangent. Nope, it just moved that airfoil. That's unfortunate. So I need to drag this. What the fuck? Okay. Tangent. That's unfortunate. So you see, every time I'm trying to set this constraint, this airfoil is going to move. So temporarily, I'm just going to select it. I'm going to fix, add a relationship to make it fixed, and then I should be able to make these guys tangent. Right, obviously, you know, that's not a good practice. You want everything to be fully defined later on, but just for the purposes of this tutorial. Then let's say you fix that bottom point with your bottom edge over here, coincident, there. And then you have your distance from the ground set, and you just have to make sure your dimensions, you know, from the inlet of the domain over here to the top surface to the exit are all large enough. Exit sketch, insert planar surface, highlight the bounding box. Okay. So it says the planar surface cannot be created due to non-planar section or open selection. That's an error with the sketch. So if you right click and edit sketch, go into this repair sketch, and you'll see gaps smaller than whatever this distance is. All right, so there's an open entity over there somewhere that we need to close, and then the next one, too. All right, so there's these two open entities. I'm not sure what's going on, but we need to close them. Ah, okay. So these two entities are open. Let's draw that line to close it. Same with this guy. Exit. And now we should be able to generate the planar surface. Boom. There we go. And there's your fluid domain with a referenced geometry off the full car. You'll note the reason we had these lines that we had to add in is because, well, we didn't do that for 2D because it's a small domain. In 3D, it's extremely hard for the CFD to sort of resolve like a trailing edge that ends at a point, right? And so an easier alternative is to just change this length to roughly 1 millimeter to sort of square off the trailing edge, and then the program will have a much easier time meshing. But I'll go into that later. All right, so that's a quick tutorial on how to generate your general 2D domain from an offset sketch, so using an intersection curve. Just gonna delete that, delete this. All right, return the sketch to its old conditions. Cool. Now back in Ansys, so we're gonna open up, have Workbench opened up. Make sure you're connected to the UCSD VPN down here. You'll see I'm connected. Otherwise, you won't have full functionality. And the program I have open is actually Workbench, not Ansys Fluent. So if I search Fluent, right, you'll see the Fluent app. But what you actually want is Workbench in this case. The reason for that is the way Ansys works is like Fluent for CFD is its own application basically, and then the other application for meshing over here is another standalone Ansys application, and it's a big pain to sort of open and close each individual application to get to your final result. And Workbench is just like a general program that combines all the functions, all the applications into a single easy to use interface. Over on the left here, you'll see all the analysis systems, or all the different types of analyses you can do. So Fluid Flow Fluent is the one we want to use. Fluent is the application that we use to actually run the CFD. Ansys also has Polyflow and CFX, and those are good for different applications, but Fluent is the most versatile and the best suited for our purposes. CFX, as an example, is very robust, but it's not user-friendly, and it's generally used for things that have propellers. So propellers, turbines, impellers, wind turbines, you get the idea. There's some other analyses types you can do. So there's a thermal analysis, structural analysis, modal, you get the idea. But so we're gonna work with Fluent. You can retitle this. I'm just gonna do 2D tutorial. In geometry, you can right click and import geometry. I'm just gonna browse. And this was the one that we made in the last video. So that was just a SolidWorks file, and you'll note we could just import that directly because of the CAD configuration that we set up in part 1. You'll see this green check mark, which means the geometry is good to go, but there's actually a couple more things you need to change. So what I did was I right-clicked and I hit Edit Geometry and Space Claim. I accidentally did that, but just right-click, Edit Geometry and Space Claim, which is sort of an Ansys CAD program. All right. Okay. So once we did right-click, Edit Geometry and Space Claim, this app opens up in the background Space Claim, and you'll see the exact geometry reproduced in SolidWorks out here. You can edit this however you want. Using I think the move feature, right? I can select this line, I can move it up and down, I can angle it, whatever. We're not too worried about that. The reason we're doing this, we need to set up named selections. So basically, you see the airfoil is facing this way, right? So this edge is going to be the inlet to our fluid domain. This edge will be the outlet. So we're saying the airflow goes left to right. Maybe we'll set this as the ground, a moving ground, and this top surface will be a free surface, which will use a symmetry function for that. But you need to tell the program what to expect later down the road. And so that's what we're here for. So we'll highlight this. Oop, let me exit. All right. Right click this and you select, let's see. I know the shortcut is Control G, but there should be, okay. There's a bunch of tabs down here. So what we're going to do is groups. So a group is basically a name that you assign to one of these edges. And in 3D, it would be the name that you assign to one face. So groups, right click this and I hit Create NS, which stands for Create Named Selection. Now we have our first one and we're going to name this Inlet. Repeat the process for the trailing or the outlet. So we click that, Create NS, Outlet. And the shortcut is Control G. So for this guy, I'll just do Control G, name it Symmetry. For the bottom, I want it to be the ground. And over here we have our airfoils. You can do them individually. So for example, I could do this one and do, wing 1, and the second one, wing 2. That's important as you start to have, if you want to look at really specific downforce values and things for the different wings. For this guy, I'm just gonna combine them. I'll make our life a little bit easier. All right, so you have all your name selections set up. You have your wing, ground, symmetry, outlet, and inlet. That's all you need to do. So you just hit save, exit out. Oh, cancel. Just hit exit out. And you should be able to continue. For good measure, you can right click this and do update, just so all your changes are reflected. Next we move to the mesh and you right click, you edit, You'll see down here, Ansys says it's starting meshing, so the standalone meshing application. All right. So once we have it loaded, then you can begin the meshing process. So for those of you who don't know, meshing basically means dividing this entire domain up into really small cells. And the CFD solver will sort of solve for the solution of the airflow, like velocity, direction, the pressure it produces, etc., at every single little cell that you produce. And basically, the smaller your cells, the more accurate your solution can be, because you can account for like a greater variation in like little velocity or pressure changes. So over on the left is a little geometry tree, kind of like in SolidWorks. What we're focused on is the mesh over here. You can just hit mesh, right click, generate mesh, and it'll do a really rough automatic mesh. And it'll give you an idea of what you should expect and what it'll look like. Boom. Right, so it's generated this quadrilateral mesh, all these square elements, and it's pretty good, or actually it's pretty trash, but what is good is that the program recognizes that, okay, these edges have smaller curves, and so we need smaller cells around them to achieve the accuracy necessary. Problem with this is these cells are way too big in your analysis. You're going to need a much finer mesh in order to have anywhere close to the right accuracy. And so to do that, you have to click this mesh box, and you have to add in some mesh control. So basically saying, okay, I want the size to be this large or this small in this area, and I want to control the growth rate. You can see how the cells are really small here, and they start growing outwards. So all that is done under mesh control. First thing is you want to add a method. For geometry, let's see. You select the entire body here, or in this case, the entire face. You have these selection options up here, just like in SolidWorks. So this is selecting a body, a face, edge, a vertex, and then this is selecting a node or an element face of a completed mesh. So this, we select the body, hit apply, and under method, you can use quadrilateral dominant, which is what's going on here, all these quadrilaterals. But from experience, I know that triangles will work better with this mesh, or for this geometry, because you have these features over here, like the sharp trailing edge, or these tight curves that quadrilaterals have a hard time conforming to. So use triangles. So obviously the benefit is triangles can conform to more complex geometry, but the downside is, you know, if you can imagine two triangles make up a single square, you're going to have way more cells, and the more cells you have, the longer your compute time to run the simulation. But since it's 2D, the difference in compute time isn't that large. It's not that important. Next, you want to insert sizing. So this is where you control, you know, how small you want the mesh to be. So under geometry, so you can do geometry selection. For example, I go to the line select tool up here over edge, and I select this airfoil edge and hit apply, and that's my geometry, and I specify my element size. Let's say I want it to be 10 millimeters. You'll see these little yellow boxes representing the approximate element size, right? So if I increase that to 20, these boxes get a little larger, and that helps you estimate, you know, how large your mesh is going to look, or how large your mesh is going to be close to your walls. Now the purpose of the name selection is actually useful here, because instead of selecting the geometry using the line select tool, which for a large like a large analysis is going to get annoying, you go to name selection and you select, let's say, wing, and it'll select those automatically. Element size is going to be your maximum size. For 2D, because I know I have the computational power, I'm going to set the max size to 12 millimeters. And then under advanced, you have some behavior here. So soft is the default, you can keep that. The growth rate, again, is how the percentage of the maximum percentage change of two adjacent cells. So they can grow by 20% larger for each adjacent cell. That's a default, and that's pretty good. Curvature and proximity are very important for your analysis, so you want to have them on. Unfortunately, that means you have to sort of specify some parameters and figure out, or to sort of set how your mesh will behave. And I'll explain what that is. So curvature basically means, so capture curvature, yes, means you want to sort of tell the mesh to very accurately draw out these curves for whatever geometry you have, in our case the airfoil. This is because you'll notice all these meshes have straight lines. The mesh cannot have curved lines, otherwise it would be much easier to conform to the surface. And so it's like, how many divisions do you want along this airfoil to have straight lines almost accurately represent the geometry? First up, you have normal angle, which right now is the default is set to 18, and what I used last year was 9. Let me explain to you guys what that is in SolidWorks. All right, so curvature angle, we'll come back to it. Local minimum size is what you can expect the minimum size, how small it can get. I'm gonna set it to 1 millimeter. And then proximity is defining how you want to handle small gaps in your mesh. So for example, we have this gap between the first element and the second element of our wing. And this is a pretty small gap. For CFD, it's important to have multiple cells across every gap. For example, if it was just one big square filling this up, you wouldn't accurately model the change in velocity between these elements. So capture proximity, yes. So the minimum size, again, is the minimum cell size for the proximity. A good rule of thumb is to just set that to the same as your minimum size for curvature. So 1 millimeter. And the number of cells across the gap is basically what the proximity function does. So I can do 4, which says for any gap, I want at least 4 cells between each gap. So 4 cells here. 3 is probably good enough for us. And then the size function sources means it'll compute the proximity from both faces and edges of the model. Bias type, I'm not sure what that is, but you can just leave that default. So the last thing we don't know about is the curvature. And curvature basically just says, given a sort of curve radius, how many divisions do I need to model it accurately? I'll explain. So let's say you have a quarter circle. Let me just draw that out. All right, so let's say you have this quarter circle arc. It goes through 90 degrees, right? So a curvature normal angle of 9 degrees means for every 9 degrees along this arc, I'm gonna have another straight line. Or I'm gonna have a straight line connecting every 9 degrees. Right, and so across a 90-degree curve or a radius, we're gonna have 10 straight lines for this arc. If I set my curvature angle to 18 degrees, then for every 18 degrees, I'm gonna have a straight line. And so for this 90-degree curve, we're gonna have 5 different elements. Let's see if we can draw this out real quick. Ooh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, let me make this curve a construction line. So I highlight all of these straight lines that I made, and I'm gonna make them equal. All right, that's a little rough. But hopefully you guys get the idea of, the normal angle for curvature means, for X amount of degrees, I need at least one element to create my mesh. All right, so once you have that, finally you need inflation. And so inflation, geometry, you just select your body. And then for boundary, you want to use your named selection, and you select where you want to grow your layers. So in this case, I want boundary layers on the wing as well as the ground. You need boundary layers on any sort of solid surface in your simulation. So in this case, we're highlighting both the ground and the wing, as those are our solid surfaces. Under inflation option, instead of smooth transition, which is kind of automatic, you need to specify first layer thickness. This gives you greater control over how many boundary layer cells you have and how thick you want them to be. So my first layer height, I'm going to do 0.02 millimeters, and maximum layers, I'm going to do 20. Now what this means is a general fluids principle is that as your fluid moves, or as your object moves through fluid, you can have a relative speed to the fluid around it. So let's say the air is going at 30 miles per hour, but as the air gets closer and closer to the wall, it's going to slow down. So at the wall of the airfoil, as an example, the fluid speed is 0. These inflation layers are a series of small rectangular cells that that model that change in velocity of the air. CFD, boundary layers. Right. So here you can see, here's a little CFD simulation, multiple airfoils. If you zoom in, that's actually eddy viscosity ratio. Right, but you can see over here these rectangular cells. That's sort of what your boundary layer is going to look like. Here's a velocity profile, basically saying that your velocity at the wall is 0, and as you go farther and farther away from the wall, your velocity u, this arrow, is going to increase, right? Very small u, getting larger and larger. So how do you know how thick your first layer should be, and how do you know how many layers you need? Here's some basic guidelines. So all of that depends on your method of running the simulation, almost like what type of math, or how you're using math to solve these fluid equations. There's two CFD models. There's many CFD models, but two main ones that we use in Formula SAE. This one is the K omega SST model, and then there's the K epsilon model. This is a quick and dirty summary. There's a lot of more information you can find online about it. But basically, the K omega SST model can be more accurate if you set it up correctly, because it fully models, it fully solves the boundary layer. As a consequence of being more accurate, it requires smaller cells and a finer mesh, and more computational power required. And some parameters you need to use for it is you want a small y plus. And y plus is another non-dimensional number like Reynolds number that you'll learn about in your fluids class. You don't have to really know what it means right now, other than for K omega SST, you want a y plus less than 5, which corresponds to roughly 20 boundary layers. Then the K epsilon model is simpler, faster, not as accurate when set up improperly, also not recommended for internal flows. But for our car, since everything is external, we can use the K epsilon model. For this, the y plus is 30 to 300, so very different from K omega, and you have 5 boundary layers. So basically, whatever model you choose will inform how you set up your mesh. And if you're asking, how do I know what y plus to target? Again, you can go into a y plus calculator online. So I just search y plus calculator CFD online. There's this one. Y plus depends on a couple of factors, like your fluid speed, your characteristic distance, viscosity of the air. I'll go into that. So let's see. Your input, your u infinity, is your external speed, free stream velocity. So let's say we set it to 14, which is almost 30 miles per hour. Or let's do 15, which is around 31, 32 miles per hour, the average speed of comp. Density of air, 1.225 is default. Viscosity, default, it's all air. Your reference length is like the reference length of your object. So for your airfoil, you'll know it's whatever we set this to. So I think it was 18 inches or 19 inches. It doesn't have to be super exact, but in the ballpark. So let's say 19 inches, 2 meters, 0.4826. So our reference length is 0.4826 meters. And our desired y plus, we want it to be less than 5. For this case, if we're doing because we're doing the K omega SST model, basically you want to err on the side of safety. So if the upper limit's 5, I don't want to target 5. I want to target something less than that, so 1. Maybe for K epsilon, I don't want to target 30. I want to target somewhere in between. Generally, somewhere around 75 is great for this. So for K epsilon, we would target a y plus of 75. But let's say we're targeting a y plus of 1. if I compute, then the wall spacing over here, this would be your first layer height. So this is expressed in meters, so we take off 3 of the decimal points. Boom, and so the first cell height should be 0.0223 millimeters. And you'll see the Reynolds number is 482,600. So as we mentioned in, I think, video part 1 or part 2, we're looking at pretty high Reynolds numbers in formula SAE. All right, so maximum layers. So first cell height 0.223 millimeters. Maximum layer is 20 because we're doing the K omega SST model and a 1.2 growth rate. You go here and you generate mesh, and you should have a good mesh when it's done. Perfect. All right, so we got this message. Some boundaries of protected topologies have been defeatured. So defeaturing means if you have a really small feature, for example, these trailing edges used to be pretty sharp, right? If we go into the geometry, let's see. Defeature just means any small, really small geometric features get almost smoothed out. So for example, over here, we have this really sharp edge over here. If you compare it to what we look at in Ansys, this edge looks a lot more blunt because of that defeaturing. Sometimes it's acceptable, but in this case, it seems a little extreme, so you want to turn that off. That's in your general mesh settings over here. So you have element size, your maximum element size. I'm going to set that to 75 millimeters. Actually, I'm going to set that to 100 millimeters. Sizing, we can turn all these off because we've specified our own sizing and curvature and proximity with these functions over here. And then defeaturing is what we want to turn off. Let me remesh it. Sorry, I clicked that kind of fast. To remesh, all you do is right click and hit generate mesh. And so now you'll see, 1, we have triangular cells, 2, we have a lot more cells, and 3, they're much smaller than before. Most importantly, when you zoom into your airfoil, you have these really small cells. You have more than 3 cells per this gap here, and looking at your inflation layers is what we defined here, right? We have, it would be pretty hard to count these layers because the first one's like 0.002 millimeters, right? But let's say we have all these like 20 layers, and it looks good, right? They go from really thin to thicker and thicker. So that's exactly what you're looking for in your mesh. So this applies to CFD, and you can apply the same principles to FEA and stuff as well. Just you usually don't need inflation in FEA. Let's see. One thing I forgot is, let's see. We're growing inflation layers on the wing. We're missing some on the ground here. We need inflation layers on the ground as well. So the boundary. Why is the ground not inflating? We can just add another inflation, a second one. Again, geometry, I select the body first, and the boundary is going to be the ground. All right. We'll just stick with the same settings. First layer thickness, 0.0223, 20 layers. Let's try it again. Okay, so you know what happened is actually the ground boundary layers looks like they're a little too thin. So instead of multiple entities here, I'm just going to do just on the wing for this guy. For this inflation, I'm going to change the ground thickness. I'm going to like change the first layer thickness to 0.1 inches or 0.1 millimeters. There. So now we have a pretty thin ground boundary layer, but it should work for our cases. And you have your wings. Once this is all set, you can hit update up here, and you'll see this saying the mesh translation to Fluent was successful. So basically the mesh has been prepared to be used with Fluent. You can close this out, go back to Workbench. Now see 2 check marks, and we're ready to go onto our CFD setup. So right click, edit, And so there are processing options here, serial or parallel. Parallel, I'm going to do 4 processes because I have 4 cores on my computer. Like, you know, with modern computers, you have like hyper-threading. You know, your computer might have like 8 virtual cores, but I'd hesitate with going much higher than how many physical cores you have based on memory requirements and things like that. Okay. Just waiting and waiting. All right. So we have our mesh imported here. It just looks like all green because our cells are so small, but you know, if you zoom in, you'll see the wing geometry. That's great. So now we need to set things up. So under general, we're going to use a pressure-based solver, absolute velocity formulation, and we're going to use a steady solution. So steady is, as you can imagine, steady state. So we're trying to see, you know, as t approaches infinity, what is the air going to look like? Transient would be like if you released a burst of air at the inlet and saw how that burst of air will flow over the wings. But for our use, we'll do steady. You can change your units and things like that here, but we set everything up in the mesh using millimeters and meters, so it'll work just fine. Models, these are different models for CFD. So you have like multiphase, energy, radiation, heat exchange, things like that. We're just doing flow, so this is like a viscous flow. So here's where you select your solving model. So you have like inviscid flow, laminar flow, but we have turbulent flow, so it falls into neither of these categories. And you select your right solver here, K epsilon or K omega. We're gonna do K omega, and we're gonna select the SST model, right? K omega SST. You can keep all these default constants in Ansys. Leave default turbulent velocity, just leave them all the same, hit OK. Now you've selected your solver. Next, you have to go to and set your boundary conditions. So this is where you sort of tell the CFD, okay, here I have an inlet of air. You know, I have air coming in at this boundary and exiting at this boundary. You can also set a moving wall. So you can say you can have the ground move at the same speed as the inlet, right? Because that's basically how we model our car moving through the air. Instead of these wings physically moving forward in the domain, we have the entire fluid moving into the wing. So ground, I'll right-click edit. And let's set our moving wall. Let's set a moving wall relative to the adjacent zone at 15 meters per second in the x direction, right? Default coordinates y, x direction. And it's a translational wall. For wheels, once you get into 3D, you can set a rotational wall, so you can have rotating wheels in your CFD. Next, inlet. I'm going to right-click and I'm going to change the type to a velocity inlet. Because we named it inlet, Ansys already recognized it as a velocity inlet, which is helpful. Great. So we're referencing from so the magnitude is normal to the boundary, so it can only go in the direction we want it to. So we're just going to set the velocity to 15 meters per second. Same as the ground. The outlet, change the type to pressure outlet. You don't have to change anything here other than selecting average pressure specification on the exit. Symmetry, right click, symmetry. And the wing is just a stationary wall. Ansys recognizes it as a wall, you can see right here. Just keep it as a stationary wall. And that's it, that's all your boundary conditions. Finally, under methods, so this is just like different parameters to tell Ansys when performing the CFD simulation to change how it will solve a system of equations across each of these cells in your domain. I like to do second order upwind for the turbulent kinetic energy and specific dissipation rate. And we're going to uncheck pseudo-transient. Like I mentioned in the beginning, this is a steady state simulation, so you don't want any transient effects modeled. So uncheck that. Leave everything else as default. And then controls, these are some different, again, some more factors you can change in your simulation. You can leave these all as default. Report definitions. If you double click that, you can create reports for lift and drag on your features, which help you sort of get an idea of how they perform. So let's do a force report of drag, and we'll select the name selection of the wing. Rename it drag. It's in the X direction, and we want to create a file and a plot. And we want to do the drag force. I guess you can do drag coefficient too, but it's just like in 2D, the reference areas and things like that are pretty rough. You know, like there is no area to reference, you know. Actually, screw it. Let's do drag coefficient and see what happens. Okay, new force report. Let's do the same for lift. Lift report on the wing, lift force in the Y direction, create a plot and a file, hit OK. Close. Now we have our lift report and our drag report. Back up here in general, I'm going to check our units and our scale to see if we can get meaningful quantities for the coefficient of lift. Let's see. Alright, I'm not sure how to do that. I would always just go with force for 3D simulations, and you can back solve to get the coefficient of lift and things like that. And so we're almost ready. Under run calculation, you double click this and you just specify the number of iterations. So let's say 200. Usually your solution will converge or be accurate after around 200 iterations, and reporting interval 1, profile update interval 1. Now before you calculate, you can just hit calculate here and it'll say the solution must be initialized before the calculation can be started. So just hit yes to initialize, and you'll see this solver down here. All right, so now we're actually starting to solve. So each of these numbers is the iteration, and you can see how the lift varies with time. It's changing quite a bit at the beginning because of these initial effects, right? But then as more and more iterations go by, the lift plot and the drag plots should smooth out and you'll get your final converged value. Residuals are a measure of the difference between each consecutive iteration. So over here, like the difference is quite large, like 1 to the 4th is like 10,000. But as time goes on, you'll see hopefully these residuals starting to decrease. So the difference between them will start to approach, let's say 1 to the negative 10th, or 1 times 10 to the negative 6, which just means over consecutive simulations, you have the same result over and over again, which you can kind of see in this plot over here as well. So basically this is what it looks like when your CFD is solving. 2D is very fast, 3D is going to be a lot slower. But yeah, you'll note that that whole process was both setup and solution. So we did the whole setup and now we're running the solution. Okay, so our calculation is complete. It says done, calculation complete. So our criteria for convergence is defined as all these residuals going below 1 to the negative 6. So technically the solution isn't converged because these residuals are not all underneath this threshold for convergence. However, if you look at the drag plots, you'll see that drag has been pretty consistent for roughly 100 simulations or 100 iterations, even more. Same with the lift. So we can say that we can trust these results are not going to fluctuate wildly. We can't necessarily say that these results are accurate because, you know, what does it mean to generate 250 newtons of lift on a 2D surface? You know, it doesn't have any physical meaning. But the value is the value in doing this is comparing different setups and saying, okay, this other setup produces relatively more lift compared to another. So over here in reports, you can get some physical values too. You don't necessarily need these plots that we generated over here. So values, you can go into forces. So forces, I can compute the forces in the X direction. So that would be drag from both of the wings. And if I print over here in the console, we have our total forces here, right? So in the X direction, you know, pressure forces, viscous forces, and total force, and total coefficient of drag. If I change the direction to the Y, print, then I have the total lift in newtons, which is not a physical number, and the total lift coefficient. Again, not necessarily having any physical meaning. Same with drag. There's also moments. So in 3D CFD, you can set your moment axes to your wheels and calculate your center of pressure that way. All right. Thanks for sticking around, guys. Almost done. We have our simulation completed, like fully done, and now all that's left is to interpret the results. So you go into results, right click, edit. All right, so this is the results of that CFD. You can use this to change your view. So this is the wing. You have wireframe turned on or off to sort of have the outline of your parts, and then you can create things like a contour. So I'm just going to name this pressure contour. So your domain is going to be all domain, and you want the location to be on one of these. Let's do symmetry 1. And we want the variable to be pressure, the global range, and the number of contours is, let me just create it. So there's your pressure contour. You can see red is higher pressure, blue is lower pressure. So we are generating quite a good amount of downforce over here, as we expect, but not as much on the second element, which is, expected. But if you optimize the spacing more, you're going to produce way more downforce and have these two really working together versus what it seems like is this front one is doing the brunt of the work right now. You can also create another contour. You can do a velocity contour. So it's just the same thing. You select the same symmetry location. If you're wondering what symmetry means in this context is, over here you have, let me deactivate this plot. You have your wireframe. You have that physical plane of your simulation, and then because it's a 2D surface, Ansys automatically generates this plane called symmetry. That's a convenient location for you to plot all of your surface contours. Oh, okay, whatever. Right, so we have pressure. We can create a velocity contour. Variable, velocity, range, global, hit apply, and there you'll see how the velocity changes. So we have our free stream velocity should be around 14 meters per second. Yep, just about. And you'll see the velocity gets quite a bit faster underneath here and slower on top. And basically faster air means lower pressure, which is exactly what we want. We want lower pressure underneath the wings to suck them down into the ground. And another, you can already see here, a reason we're not producing as much downforce as you might expect on the second element is we're getting the separation from the first element. And on the second here, these blue streaks means the flow is separating. And if these were working together well, then the velocity would stay continuously attached, and you'd produce a lot more downforce. So there's some contours you can create. There's also streamlines. So there's these streamlines. I'll start it from the inlet. We'll go 25 points, hit apply, there. And you'll see a representation of how the streamlines go along your object. You can increase your number of sampling points, let's say 250. Boom, and you get a better idea sort of not only the velocity of the streamlines, but the shape of the flow. You can layer your graphs on top of each other. I can have streamlines and velocity layered. I can even change the transparency. So let's say I make my velocity graph. I'm going to go to render and increase the transparency to whatever that is. Right, so you can layer things on top. You're not limited to just visual things here. You go to calculators, function calculator. You can calculate, like we did in the solver previously over here. You can calculate things like pressure or your forces, your force. I want my force on the wings globally in the x direction. Boom, so it's 7 point whatever newtons. Again, this is not a physical number, but it's a representative. And then I can change it to the y direction, and there's our lift. All right, so that's your intro to 2D CFD. Thanks for sticking around for such a long time.